Hello everyone, welcome to this the morning session. I'm very glad to introduce Professor Hong-Yi Lee from National Taiwan University. I think everyone knows him already, but I just want to kind of explain some of my kind of personal interaction with him. So as you know, that he's kind of a leading researcher now, but I met him in 2010. Already he was very visible when he was the student there. And then I had a lot of interactions with him. I learned from him about his kind of work on the combination of the speech recognition and the spoken language system and so on at that time. And then since then, we kind of continued the interactions. And recently, we also had a very great experience of making a benchmark with the Hong-Yi, which some of you may know the SPRG, the benchmark, which is also kind of for me the very good memory. So based on his kind of good kind of very kind of how to say, foreseeing the visions, the organization leadership, the Hong-Yi, our group, Hong-Yi's group, the Meta's group, Amazon's group, we really enjoyed to create a kind of a benchmark, which is nowadays used as many of the researchers here or as a kind of founding the speech self-supervised learning model, which is, I say, one of the kind of start of the speech foundation models. And then since then, Hong-Yi is kind of leading this community and providing a lot of kind of interesting kind of research directions and today's talk. So yeah, let's welcome Hong-Yi.
Thank you. The mic is there, or you can just be loud.
I can be loud. Yeah, I think it should be loud, right? Yeah.
Yeah, thank you very much for Shinji for the very nice words. So it's my great pleasure to be here. So this talk is about teaching large language model to listen and speak. So since this is the first talk in this workshop, I would like to sorry? Oh, hide this one, right?
This one.
Okay.
There's some option, though I don't know about there's some way.
On Windows, it's Control-Alt-Shift-H to hide everything.
No, I know. Okay, it's already gone. Okay. Okay, so since this is the first talk in our workshop, I would like to introduce what is speech large language model a little bit, because I believe we will hear this term or other similar term like spoken language model, audio language model again and again in this workshop. So I think it's good to have a very, very brief overview to share with you when people talk about speech language model, what do they refer to? So actually speech language model can refer to a very broad family of models. So when we talk about speech language model, the model has two capability, either one of the two capability. The first one is the model can be speech aware. That means the model can take speech as input. And the second one is the model can generate speech signal. The model can use speech signal as the output. If a model have either one of the capability, usually people call it speech language model, but of course many model can have both capabilities. And when you listen, when someone mentions speech language model, you have to be careful. You have to be very careful. What can the model do? So different speech language model target at different purpose. Some model want to do conversation. So you give it an input, you say, hi, I'm Hong-Yi Lee. Then the model responds with, hi, Hong-Yi, nice to meet you. Some model target at continuation. So you say, I'm Hong-Yi Lee, then the model continue with a professor at National Taiwan University. And usually this kind of continuation model serves as the base of the conversation model. But there are a lot of research focused on develop this kind of continuation model to make them better. And there are some model targeted at speech analysis. So this kind of model take an utterance as input, and there would be a text instruction or speech instruction to tell the model how to process the input speech. For example, given an utterance, if the instruction is, what is the speaker's emotion? Then the model have to output happy. So this is also different from conversation and continuation. The model process the input signal. And there are some speech language model target at specific tasks like TTS or voice conversion or voice editing. So when someone talk about speech language model, they can refer to different things. So be careful. So you have to consider what is the model built for. And you also have to think about what does the model know about speech. Let's take a conversational model as an example. When I say I will give a talk at the TTIC workshop, if the model can understand the content, then it can reply with, for example, nice. However, if the model has some idea about the emotion in the speech signal, and probably the model will identify that the speaker sounds like very nervous, then the model can respond like, don't be nervous. Or if the model can identify the environmental sound and the model heard something breaking, then the model probably can respond with, are you okay? Instead of reply to what you say, the model is more careful about your safe. So the model probably would ask, are you all right? What is happening? So you have to consider what does the model know about the speech. So let's start today's talk. I have 3 major topics. The first one is how to start from a text model and fine-tune the model so the model can take speech as input. And for the second part, the model not only take the speech as input, but can also respond with speech. And for the third part, the model can do reasoning. So let's start from the first part. So at the beginning of each part, I will provide a model profile so you better understand what kind of model we are developing. So for part 1, the model is speech aware, but it's not speech generation. And this model is targeted at speech analysis, and we hope the model can understand the speech signal from all aspects. Hopefully, with large enough training data, the model can understand all aspects in the speech signal. So here we are going to start from a text language model. We are going to teach a text language model how to listen. As you know, text language model can take text as input, response with text, but they cannot understand signals originally. You need to have a speech encoder to transform very sophisticated speech signals into speech representation. And you have to fine-tune the text language model a little bit so it can understand the input representation. Usually what people do is insert some adapters into the language model, and you only fine-tune the parameters in the adapters. To train the parameters in the adapters, you need to have some training data. A very typical way to train this kind of adapters is to prepare some speech-related text. You tell your text language model, please describe the utterance, and the ground truth should be, how are you? And if the instruction is, please identify the emotion in the audio, then the output should be happy. Hopefully, if we collect sufficient speech-related text to train the adapters, then the model can understand the input speech signals from all aspects. We start this project very early in 2023. At that time, there is no benchmark we can use. In order to advance this research direction, Xinji and I initiated a project called Dynamic Super. We want to build a benchmark for spoken language model. So in Dynamic Super, what we are targeted at is build an evaluation benchmark for speech language model, and each example contain and text instruction and input speech signal and its ground truth. The first version of Dynamic Super includes 555 different tasks. Then later, David Howard's team joined the second phase. In the second phase, we extend to 180 different tasks. And we not only include speech-related tests, but also music and audio tests. And you can find that this is the taxonomy of the benchmark. It's very sophisticated. So for speech, we have main category. For main category, we have subcategory. For subcategory, we have subcategory. For subcategory, we have subcategory. So it's a very sophisticated taxonomy. And tomorrow, we will have more investigation about the benchmark of spoken language model. So scan the QR code here to join the cooperative activity. So we already have the benchmark, so we can start to train the model and evaluate the model. In our preliminary study, we have some in-house training data. They include 23 different tasks, and we use this data to fine-tune the adapter in the language model. Then we evaluate the model on dynamic super. In dynamic super, there are some unseen tasks, means this task has never been seen before during the training time. There is some seen task, there is some task exists in the training data, but the data points are different. The data examples are different. This is some preliminary result. So our preliminary results seem to be very promising. Here we show the average accuracy in the different categories of dynamic super. Larger the value means higher the accuracy. Here, the blue bar is the result of random baseline. So if a model is worse than blue bar means it's very, very worse. Then for the green bar is a cascade model. We cascade an ASR model and a text language model and see how good this kind of model can achieve. And it is expected that this model cannot achieve good performance on all the categories. For example, in the speaker-related task, this kind of cascade model achieves very bad performance. But this is expected if you only transcribe the utterance into text, and there's no way for the text language model to know anything about speakers. Then we have the encoder and the text language model. We have the jointly trained model. We fine-tune the adapters, and we get the performance in the yellow bar. You can find that we get pretty decent performance in several categories. However, if we analyze the performance of the model more carefully, we found that the model overfit to the same data. So usually the model achieves good performance on the test it has seen before, but for the test it has never seen before, the model usually gets very poor performance. So it looks like the model overfit to the training test we have. This is reasonable. We only have 23 training tests. A potential next step is to collect as many tests as possible, hopefully with sufficient speech-related training tests to train the spoken language model. The model can have emergent capability, and in the end, it can solve all types of speech-related problems. However, we try another research direction. This research direction is called descriptive speech-text alignment. It's mainly leading by my PhD student, Ke Han, and a group of NVIDIA researchers. So the first finding is we consider it is not necessary to collect a large amount of speech-related tests. Training speech-language model on one test is probably sufficient for it to generalize to other tests. So the single test we train the speech-language model is audio captioning. For audio captioning, which means the model take an instruction, describe the audio as input, and it has to describe the information in the input audio as detailed as possible. For example, it has to mention something about speaker characteristics, it has to transcribe the input, it has to mention something about the prosody, it has to mention something about the emotion in the input audio. Probably you would ask, if we train the model only on audio captioning, can the model generalize to the task it has never seen before? At the very beginning, we find that if we train the model on audio captioning, the model just fit on the audio captioning. So this is a real example. After we teach model how to do audio captioning, then we ask the model what is the gender of the speaker, then the model just ignore the instruction and do the audio captioning itself. But then we found that there is a tip to make the model less overfit to the training test it has seen. This tip is from SLMs, and the tip is like this. You multiply the output of the adapter with a constant alpha, which is smaller than 1. And this will make the adapter has less inference and the model generalize well. So this is some result. If we set alpha equal to 0.75, then the model start to answer questions. Even though during the training time, we only train the model on audio captioning, Now it can answer the question if we modify the output of the adapter a little bit. Alpha set to be 0.5, the model still answer the question. Of course, the alpha cannot be used more. If you set the alpha equal to 0, then this is not a speech language model. The model cannot understand the input speech at all. So this is the first phase of DESTA. Then we move to the second phase. In the second phase, we even find that this trick is not necessary. If you create the audio captions, if you create the ground truth of the audio captions carefully, then you don't need the alpha kit. So what do I mean by properly created here? Here I mean, if the audio captions, if the ground truth of the audio captions are generated by the text language model, you are going to fine tune to be a speech language model, and you train on this kind of data, then the model will not fit to this kind of data. After the training, it can generalize well to the new text it have not seen before during the training time. So this is the whole framework of DESTA2. Given all the training options, we have some labels. We know the information like transcription, gender, emotion, accent, and so on. And we give the text language model this attribute label. Since these labels are text, so they can be the input of text language model. And we ask the text language model, what can you hear? Then the text language model will pretend it really hears something and generate the audio caption. And we use the audio caption generated by text language model as the training target of the spoken language model. So we fine tune the adapter here, the text language model, the whole spoken language model, take the transcription, what can you hear as input, and it has to output the audio caption the same as the text language model. And a very important tip here is the text language model used to generate the audio caption should be the same as the one you are going to fine tune to be a speech language model. I will show you some experimental results here to support this claim. And during the training time, we only train the model with the instruction, what can you hear? So this is the only thing we teach the speech language model to do. But to our surprise, during the inference time, you can ask the model any question, and potentially the model can answer your question based on the instruction. And recently, we have DESTA 2.5 with more training data than the second version. We use Llama 3.1 as the backbone, and we gather some public available data with 5,000 hours of speech data, some environmental sound data, and a little bit music data to train the model. And here are the attributes we have. And the model is already open source. I also put the link in this page. So this is some results I would like to share with you. So we evaluate DESTA 2.5 on several benchmarks. We first evaluate on dynamic super, and it gets good performance compared with other models. And I have to highlight that we only use 5,000 hours of speech data, and lots of spoken language model use probably 100 times more training data than we have. And we also evaluate the model on NNAU, and it also achieves some good performance on NNAU. And we also submit the result to the leaderboard of NNAU. And here is DESTA 2.5 rank 4 in the leaderboard. And other model ranked above us are from big company. Flamingo from NVIDIA, Q1 from Alibaba, and Gemini from Google. And we do not really rank better than this model because you can find that our model is very poor at music, but this is reasonable because we have very limited music training data. If we only compare the performance in the speech domain, actually DESTA 2.5 are comparable with other models. And we also evaluate the instruction following capability of these spoken language models. So this is a benchmark created by my PhD student, Ke Han. And this benchmark is targeted at the instruction following capability of the speech language model, because we find that lots of speech language model, they have worse instruction capability compared with text language model. If you ask the model, what emotion is the speaker expressing, usually the model can provide an answer. However, if you add some extra requirement like answer in capital letters, this is a very simple requirement, but you can destroy the model. Some models start to do ASR if you add some extra requirement. So we want to evaluate the instruction following capability of the models. So this is some result. The red dots here are the instruction following capability of the text language model. Then the blue dots here are the instruction following capability of the speech language model. So those text language model are fine-tuned to be the speech language model here. And you can find that after fine-tune the text language model to understand, to analyze the speech signal, the model is not as good as their text counterparts when following the instruction. But for Delta 2 and Delta 2.5, if you train your model with the strategy we provided, then the model have very little degradation in terms of instruction following capability. So for the first part, the last experiment I would like to share with you is use which model to generate the training data is very critical. Here we use Llama 3 as our backbone, and we try to generate the audio captions with different models. We try Llama families, Q1, and Gamma. And we found that if you use Llama family to generate the audio caption in ground truth, then you get much better result compared with the data, using the training data from Q1 and Gamma 3. And here for Q1, we put not available here because after we fine-tune the model with the ground truth generated by Q1, then performance becomes so poor. We just break the model, it cannot get anything. Probably you will consider, is this because Q1 cannot generate proper training data? This is not the case. If we change our backbone model, here the same training data from Q1, but we change the backbone from Llama 3 to Q1 2.5, then we get much better performance, even better than the performance using Llama 3 as the backbone. So this experiment showed you use which model to generate the ground truth is very critical for the success of the speech language model. So this is the first part. Then let's move to the second part. In the second part, we are going to talk about speech input and speech output model. So this is the profile of the model in second part. It's speech aware, it generates speech. And here, what can the model do is continuation. And hopefully we want the model to understand all aspects from the input speech signal, but we do not really have the comprehensive evaluation. Here I have two slides to remind you how language model can generate speech. The basic idea is you transform the waveform into a token sequence by a tokenizer. Then you train a language model to generate the speech tokens. The model generates speech tokens autoregressively. And after the model generates a token sequence, you have the tokenizer to take the token sequence as input and generate the waveform. And of course, you can use this idea to train a speech language model. You only have to collect a large amount of data, probably from the internet. And if you only want to build a model for continuation, you can directly train on any audio data you can collect it. Then you can have a language model that can do the continuation. But then we found that training a language model only on the speech token is very challenging. This is what we can get 2 years before. So this is a pre-trained language model which can do continuation, and this is its input.
He assassinated the president.
Someone say he assassinated the president. Then what would happen after someone assassinated the president?
And gave him, Mr. Johnson, the last charge of improvement in his writing possible 3.89.
I know this sentence is very hard to understand. I asked ChatGPT, does this sentence make sense? ChatGPT say this sentence doesn't really make sense. And this is usually what you get if you train your speech language model only by speech tokens. Some researchers in Meta told me that even though they have tens thousands of hours, 100,000 of hours of audio data, they cannot get very good speech language model if they only train the speech language model on speech tokens. And nowadays, people already realize that if you start from a text language model, then it is easier to get a good speech language model. So if you start from a text language model and teach the text language model to generate speech tokens, then the model can generate not only speech token, but also the text token. This is the original capability of the text language model. So the model can generate both speech and text tokens. So during the generation time, you can do text and speech hybrid generation. The model not only generate text token, but also generate the speech tokens. And the detokenizer take the speech tokens as input and generate speech signals. And even though those text tokens would not be used for generated speech, they are very useful for make the generation have the good performance. This text token can serve as the inner monologue, address as what the model wants to say. And the idea of inner monologue is from the paper of Moshi, and I believe you will learn more about Niall in the later invited talk. The challenge here is text token and speech token, they have very different length, and their alignment can be very sophisticated. Usually, the speech token sequence are much, much longer than the text token sequence, and their alignment is not straightforward. To deal with this problem in the literature, there are many different strategies for text and speech hybrid generation. Different sites invent different approach to generate text and speech hybrid sequence. And here, I'm not going to go through the detail. Here, I'm going to consider another direction. If we are going to use text and speech hybrid generation as our generation paradigm, can we reconsider the design of speech tokens? Today, when we train the speech tokens, speech token tokenizer and detonizers, we do not consider the decoding process. However, if we already know that we are going to use text and speech hybrid generation, and actually the decoder here, the detokenization here, can not only take the speech tokens as input, but also the text token as input, because it's already generated by the model. So the decoder tokenizer can take the text tokens as input to enhance the generated result. If this is the case, then these audio tokens do not have to include the content information. It is redundant to put the content information in the audio token because you already have the text tokens to include the content information. So I know nowadays when people evaluate or create speech tokens, we want the speech token to include everything about speech, including the content information. But here I want to point out is, if we are going to use text-speech hybrid sequence, probably we only need to include something cannot be expressed by text in the audio tokens. So this is the first consideration. The second consideration is the audio tokens do not have to be fixed duration. Can we have dynamic duration audio tokens? And if we have dynamic duration audio tokens, we can make the relationship between text and audio tokens more straightforward. For example, can we have one speech token corresponding to one text token? What I mean is you have a tokenizer, take the utterance as input, and if this utterance have 3 text tokens, can we also only generate 3 corresponding audio tokens, each audio token corresponding to a text token? If this come true, if this is possible, and if we can make the relationship between text and audio tokens straightforward, then the hybrid generation can be very easy. The speech language model only have to generate 1 text token, 1 audio token at a time. You do not have to worry anything about the alignment. The speech language model only have to learn to generate 1 audio token after a text token. Can we achieve that? So here we propose an idea called TASTE, and this is done by my PhD student Liang Xuan and cooperate with researchers from MediaTek. So this is the idea. So this is the input utterance. we use the typical pre-trained speech encoder to extract the representation from the speech encoders from the speech signals. So this representation are still corresponding to a fixed period of time. Then we assume we have an ASR model, so we can transcribe the input utterance into text token sequence, and we have an aggregator consists of several attention layers, and we consider each text token as a query. And we consider the representations from speech encoders as key and value. And each query will gather the information from the representation here. So given an utterance is represented by a sequence of representation, and each text token here gather the information from the input sequence and output an audio token. So each text token corresponding to one audio token. So there are 3 text tokens. So the aggregator will output 3 audio tokens. Then for our detokenizer, it's similar to a TTS model. It will take the text information as input because it takes the text information as input. So hopefully those audio tokens will not include too many text information. And different from the typical TTS model, here the decoder have the audio token to describe how to pronounce each text token. So this TTS model not only takes the text as input, but there will be an audio token to describe how to pronounce each text token.
Can you generate output that's not the same as the input?
Sorry?
Can you generate an answer to this question instead of repeating how?
No. So here we are training a tokenizer. So here what we only do is transform speech signal into token sequence. Then we are going to train a language model on top of the token sequence. Then the model can generate something different, for example, answer the question. So here we haven't trained the language model yet. I will train the language model after a few slides.
Okay, so which part would you consider as the tokenizer?
Okay, so what is the tokenizer? Here we consider the pre-trained encoder plus the aggregator as the tokenizer. So this tokenizer takes an utterance as input and it outputs some token, and the token number is the same as the transcription of ASR.
Okay, thank you.
Thank you. And train this tokenizer is the same as the typical way to train the tokenizer by minimize the reconstruction error. So this is the idea of test. So before we show, yes, please.
Here, to get the tokens, you also need the text, right? Like computing speech recognition, because you're doing. So what if there's like a mistake in the text, like how are you? The speech recognizer is saying, "Who are you?" And then have you attempted to see if the alignment between the text and the speech is not correct? Is the quality of the tokens degraded?
Yeah, this is a very good question. We do have the experiment to compare the result with and without speech recognition errors. When we train the model, on ASR transcription. So potentially there is some error. We find that if we use the ground truth, actually we get slightly worse performance in our downstream spoken language model, because the model is already fit on this kind of error, transcription with the error. So actually have some error, get slightly better performance. But there's other question people usually ask. It looks like this model is text-centric. What would happen if there are something they cannot be represented as text? For example, someone coughing, someone laughing, probably typical ASR model do not have the token corresponding to this kind of phenomenon. So I think this can be a future research direction. At this moment, my answer can be, there are some ASR model, they can output symbols represent the non-verbal information. So some model can output a symbol called laugh. So our approach can still be useful in that case. But for module case, yeah, please go ahead.
You consider also the issue that you need to retrain every time the tokenizer when you switch the language model.
Switch the language model?
Because you need to have the same tokens as language model, right?
Yes, yes.
The vocabulary. So
yes.
Now if I switch from llama to Qn, I have different vocabulary.
Yeah.
So that means I need to retrain tokenizer here because I need to have another vocabulary for the text.
Yes.
Using.
Yes, this is the current case. Okay, so before we train the language model, here I'm going to share with you some results about the analysis of the audio token. So we have a simple demo to let you have some idea what those speech token include. So we have a very slow utterance.
The captain's face had been buried in a pile of papers. But now Murdoch came around to stare at the gang leader.
So someone speak very slowly. So for the second utterance,
Any news on the Dancer assault case?
it's very fast.
Any news on the Dancer assault case?
So someone speak very, very fast. And these two utterances has the encoder and get the token sequence. Then we switch the tokens between two utterances. So for the tokens, audio tokens for can around Q, we replace with the tokens of new sounder. For the token of new sounder, we replace them with the token of tense round Q. Then we pass the tokens through the tokenizer, then we can listen what we get. So this is the lab example.
The captain's face had been buried in a pile of papers. But now Murdoch came around to stare at the gang leader.
So can you tell the difference? Let me play it
The
again.
captain's face had been buried in a pile of papers. But now Murdoch came around to stare at the gang leader.
So can around Q is speed up. For the second example,
Any news on the Dancer assault case? Any news on the Dancer assault case?
so you can find that the new sounder is slower. But this is not what we really, this is not our final target. Our final target is train a speech language model. So we use the media as a training data set. We use English subset, only have 40,000 hours of data. We have the transcription, and we can extract token corresponding to each text token. Then we can train a speech language model. Each time the model will output a text token. Then after the text token will be an audio token, one text token, one audio token, and so on. And we use Llama 3.21 billion base as our initial text language model. This is not a very powerful text language model. We have limited computing resources, so we cannot train the model larger. If you are interested in this idea, feel free to try to train the model on, try to use a larger base model to implement this idea. Okay, so probably I can skip some boring number. Let's directly listen to the demonstration. So this model can do continuation. So given an input,
I'll take the armchair
then it will respond, it will continue.
in the corner and just sit there. It'll feel better. I'll try to not sleep.
And this is another example.
I reserve your services
And this is the continuation.
for a long time. I am very happy with the result. I will definitely recommend you to my friends.
So you can tell that compared with what we can get in 2023, the sentence is much semantic coherent. And now with this model, I can try all different random things. So I cut an utterance from Big Bang Theory.
It's hot and loud and there's so many people.
So this is sentence from Rajesh, and this is the continuation.
I don't know what to do. I'm not a fan of crowds. I'm not a fan of loud music. I'm not a fan of being in a crowd. I'm not a fan of being in a big city.
So another example I try is this one. Probably many of you have heard this quote.
Look at my eyes!
Look at my eyes. So this is from a content creator. If you have ever known this quote, then you know its ground truth is tell me why, baby, why. So let's see what's the continuation of the model.
I'm not the one who's wrong. I'm not the one who's wrong. I'm not the one who's wrong. I'm not the one who's wrong.
So the model wants to emphasize is not the one who's wrong. Yeah, I also try lots of random things. So I try this one. So I'm not sure whether everyone knows this mean. So I do prepare the video. I want So if I were a speech language model, what I would learn is if someone say hi, then I have to continue with Nani Gaski. This is the only Japanese sentence I learned today. Is what do you like? So let's see what the model will continue. Of course, model cannot say Nani Gaski because we only train on the English data set. So this is the Ruby John's voice. And this is the continuation.
I'm Ruby, a third-year PhD student in the Department of Computer Science at the University of Cambridge. I'm currently working on a project to build a language for describing and reasoning about security policies.
And I also try other characters. This is Ayumi-chan.
I'm a new member of the club. I'm from Japan. I'm studying in Australia. I'm a big fan of anime.
So the last one is from Shiki-chan. So this is the continuation.
I'm the host of the podcast, Girls Guide to Travel. I'm a travel writer, photographer, and educator. I've been traveling the world for over a decade, and I'm passionate about sharing my experiences with you.
Yeah, I know what Shiki-chan says is a little bit weird, but you can feel that the model can continue differently from different heights.
I have a question.
Okay, yes.
So your tokenizer is trained with paired text and speech.
Yes.
But here, because you're doing generation, you don't have the corresponding speech for the tokenizer to attend to.
No. So during the training time, the model will learn how to do continuation. So the model will learn how to generate the tokens corresponding to the ground truth. But during the inference time, of course, we do not have the ground truth. So the model have to generate the audio token itself. These are invented by the model, and the tokenizer take both the text and audio tokens as input and synthesize what you hear.
So it actually generates both ASR tokens and audio tokens.
Yes, exactly.
Yes, so for all these speaker voice and intonation, they kind of similar to your input. So I was just wondering, all this information are captured, are encoded by your pre-trained encoder?
So this is a very good question. Actually not. So in our paper, we do use the speaker embedding for the, so we did extract the speaker embedding from the input utterance, and the decoder also take the speaker embedding as input. So I think the speaker information is mostly included in the speaker embedding. So the audio token mainly focus on something related to processing.
Thank you.
Yes, please.
What's the relative size of the vocabularies for text and audio tokens, and how much does it matter? Like, did you do a sensitivity analysis to see, should I have more audio tokens in vocabulary or less, or?
We do have some preliminary study. If I remember correctly, here the number of audio token is not very large. We have 4 layers of tokens. Actually, we use multiple layers like RPQ, and each layer have 512, if I remember correctly. We do not really have the computing power to try all the different setup. So if someone interested in this, you can try all the different setup to get better performance. Okay, David?
So another follow-up question I had, thinking about, the speaker embedding that you use combined with the audio tokens, combined with the text. I wonder what your thoughts are on using these learnable speech tokens as opposed to something kind of like, well, let's say you just extract typical prosodic features, intensity, pitch, duration for each word. You concatenate those with speaker embedding text.
Yeah.
Do you think that there's something more besides that?
Very good question. I don't have answer at this moment. This is probably something people can investigate in the future, because nowadays on those speech benchmark, usually if you concatenate lots of different models, so you not only use ASR, but audio captioning model, you also extract the prosody, you also have an emotion recognizer to detect the emotion. You give all kind of text information and give it to a text language model, and ask the text language model to answer the question. It's the top line on dynamic support. None of the model can beat this top line nowadays. So I also wondering how necessary is to have the audio token. Can we really get very different information from those other detectors? But this is something we can investigate together in the future. All right, the last questions.
You test like compared with the TTS, which prefixed with the original speech, and you do continuation in the sense of knowing that maybe your tokens contain just, exactly the same information as a basic TTS.
As the basic TTS?
In standard TTS, we do the text only, but we also now can do controllable generation where you prefix specific speech.
Yes.
So I wonder if your audio tokenizer is doing better than the controllable generation in TTS.
I see. And this is a good question. So I know today, if you want to have a speech language model, there are many different ways you can realize it. Here we have a more end-to-end fashion, but someone can also have, you have a text language model, it output something to the TTS model. So TTS model takes the text as input, and audio language model also outputs some representation to the TTS model, and you can train the TTS model and the speech language model and end-to-end.
Yeah, so my question kind of, understanding if your tokenizer is doing better in terms of extracting the proper audio tokens in the sense that you extracting actually dynamics, how the pronunciation changes over the time, or you're just mimicking actually the initial, prefix similar to the controllable generation in TTS.
So in my point of view, our whole method is very similar to controllable TTS. So you can also understand our approach as jointly train a controllable TTS with an text language model. And text language model can output something, some fine-grained tokens. Controllable TTS have very different types. Some only controlled by an embedding, but here our controllable TTS is controlled by fine-grained tokens, and our language model can output fine-grained token to control a TTS model. Actually, our decoder using the same architecture as Cozy Voice. So you can also consider it as a controllable TTS model. Okay, so I have the last part. I really want to finish the last part. Please allow me to finish the last part. So the third part, we are going to talk about a speech-to-speech language model, but with reasoning. So this is the model profile. The model is speech-aware and speech generation. Here we are going to do dialogue, means the model can respond to your input. And for what does model know? Here, the model probably only know content information because this is only what we train, but we only have the content related training data for the model. So everyone know that today you can use reasoning process to enhance the text language model. So we can do the same thing for speech-to-speech language model. From this slide, I will not show the hybrid generation, but actually here the token sequence include the text token sequence. Here the speech token sequence actually include the text token sequence. We do hybrid generation here. So for a speech language model, instead of just take speech as input and response with speech, can we also add a reasoning process to improve the generation result? This reasoning process can be just a sequence of text tokens not shown to the users. And there are already some literature try this idea, and it has shown that reasoning can improve speech language model. But what we are considering here is about the latency. If the model have to go through the whole reasoning process before it start to say something, then there is a very low latency. The user have to wait for a while before the model start to do the interaction. So here we are consider another idea. Can the model speak and reasoning at the same time? So the user do not have to wait for the model to do the reasoning. Originally, I think this is probably a very challenging task. Probably we need to invent some new network architecture, probably two decoder with some cross attention to really make the model think while talking. But then we found that you do not really have to invent a new architecture. The current language model is good enough to achieve that. So here is our idea called Stitch. It's proposed by my PhD student Chen Han and a group of Microsoft researchers. The idea is this. Let me use GLM for voice as an example to describe the idea of Stitch. In GLM for voice, each time it generates 39 tokens. 13 of them are text token, 26 are audio token. Then you have this audio chunk. You have the tokenizer to transform this token chunk into speech waveform. Then the model, the platform start to play the speech waveform. And while the audio is playing, the language model have to generate another chunk of audio token, and another chunk of audio token will be synthesized into speech. Then you will not feel there is a gap here if the tokens are generated fast enough. Can the model generate the tokens fast enough? Actually, it is, and it's too fast. To generate 39 tokens on A100, you only need 0.5 seconds. And if you have 39 tokens, they are corresponding to 2 seconds of waveform, and you only need 0.5 seconds to generate the audio tokens, that means you have 1.5 second buffer. There are 1.5 seconds, the model do not have to do anything. So how about we use this buffer to do the reasoning? Let the model generate some reasoning token in this 1.5 second buffer. 1.5 seconds is already good enough for the model to generate 100 reasoning tokens. So this is the basic idea. So typical way to use the reasoning is input, reasoning, and output, then generate the waveform. The user had to wait in this scenario. Here we propose stitch. The idea is input, and the model first generate a segment of audio tokens, then transform into speech signal. While the speech signal is played, generate the text token for reasoning and some audio token for synthesize, and synthesize the next audio clips. So this is the basic idea of stitch. So another issue is how to prepare this kind of data. So there are already lots of speech input and speech output training data. And we have the text transcription, and we ask the text language model to write the necessary reasoning process between the input and output. And we segment the reasoning process into chunks. Each chunk have 100 tokens. We also separate the speech output sequence, and we teach the model generate first chunk of audio, then reasoning, then second chunk of the audio, second chunk of the reasoning tokens, and so on. So the model can do reasoning while speaking in this kind of design. Does this idea work? We fine-tune GLM for voice. We use GLM for voice as our base model. And before we say something about reasoning, we fine-tune GLM for voice on our own data set because we have some extra data. Probably GLM for voice have never been seen before. So probably the improvement is not from reasoning, but from the extra data. So extra data do improve the performance. Here I show the accuracy. So this is the accuracy on several math problems, speech-to-speech math problems. So the improvement from 53 to 63. So more data is helpful, but reasoning is even more helpful. So if we add the reasoning process with the same training data, the performance improves from 63% accuracy to 79% accuracy. Then how about stitch? If we implement stitch, the performance degradation is pretty tiny. We only degrade the performance from 79% accuracy to 78% accuracy. And I have to highlight that stitch do not have any latency for reason. So the latency in this bar and this bar are exactly the same, but there are a large amount of improvement if you add the reasoning process. And I also want to mention the audio quality is not influenced. And we also have other considerations. What would happen if during the inference time, your model, your GPU is not as good as A100? If you have a slower GPU, then you take longer time to generate audio tokens, then your buffer becomes smaller. You can only put less reasoning token in a smaller buffer. If our reasoning tokens are less than what we have during the training time, then what would happen? So here is the experiment. During the training time, we always have 100 tokens in each token chunk, but during the testing time, we have the reasoning chunks less than 100 tokens. And this is the experimental result. Here I show the result on different corpus. The horizontal axis are the number of tokens in each reasoning chunk during the inference time. And we found that if we have shorter reasoning chunk, of course, the performance becomes worse. However, if we compare the performance of reasoning and the performance without reasoning, the dots here are the result without reasoning. We can find that in many cases, reasoning improves the performance. And here we are also consider what would happen if the reasoning process is from another model. Let's say you have a very powerful text model which can do reasoning very well. Can we leverage the reasoning process from a text language model? The idea here is you have a speech language model, take speech as input, and it generates something. Then the text language model take the input, take the speech input. You have the ASR, so you can transcribe speech input into text. So the text language model have text input, and it also takes the output of speech language model as input, because here we have hybrid decoding. So there are some text tokens, so text LLM can understand this text token. Then text LLM output the reasoning process, and speech LLM read the reasoning process and generate another audio segment. So let's see if the reasoning process is generated by other model, what would happen? So here, the red line is the result using speech language model itself to do the reasoning. Then this purple line is we use GLM for 9 billion chat, which is a more powerful model compared with our speech language model to provide the reasoning process. You can find that if we use a text language model to generate better reasoning process, the overall performance is improved. Then if you have a worse model to generate a reasoning process, then the performance will become worse. And we consider this as an evidence to show that this speech language model to rely on the reasoning process to make the result. If the reasoning process is bad, is not reasonable, then the model will get the wrong answer in the end. Here, this is the last slide of my talk. Here is the demo of speech.
Claire makes a 3-egg omelet every morning for breakfast.
How
many dozens of eggs will she eat in 4 weeks?
And the model answer?
Claire makes a 3-egg omelet every morning, and there are 28 days in 4 weeks. That's 84 eggs in total. Since there are 12 eggs in a dozen, she'll eat 7 dozens of eggs in 4 weeks. The answer is 7 dozens.
So you can find that on this screen, there are some green tokens. The green tokens are reasoning tokens. They are the reasoning process of the speech language model, and they are only generated behind the scene. The speech language model do not read this reasoning tokens. So this is all I want to share with you today. So thank you very much for your attention.
Maybe we can accept 1 or 2 quick questions.
Okay, regarding your last part, you showed that if you do the reasoning, alternating reasoning and generation, the performance was not degrading. I wonder if there are cases where it should actually improve, because it looks at not only the text reasoning, but also the audio that you generate.
I see. This is a good question. You think because the audio model also generates an audio token, right. So the model can also leverage the audio token to improve its performance. We do not observe this phenomenon, but what we observe is like this. Sometimes the model will put the reasoning process in the audio chunk, because we have limited token in the reasoning chunk. If the reasoning is not finished yet, then during the audio segment, the model will try to do the reasoning that is not completed in the audio chunk. However, if we analyze the chunk between chunks, you will find that the result is continuous. The model will not have very discontinuous result. All the audio chunks put together would be some like a fluent sentence. You will not consider the model actually do reasoning behind the scene.
So during training, you probably fix the token length of the chunks, but during generation, you don't fix that.
During the generation, we let the model to output the token called end of reasoning, then you end the reasoning chunk. And I believe in most cases, because during the training time, there is always 100 token, then end of token. So during the inference time, probably model also do the same thing.
Okay, thank you.
Thank you. So we need to finish kind of a presentation. So thank the Hong Yi again.
Thank you.